Hi, everybody, and welcome to Down to Earth. I'm Eric Edelman, your host for this evening, and thank you so much for joining me for our first show back from the hiatus. We're officially returning to our weekly schedule, so if you enjoy this type of content, we will be around for a while. If you're new to what we do here, this is a show where we take astronomy topics and relate them in one way or another to our own human experience. And we've done shows on what it would be like to, say, experience a gamma ray burst for ourselves. And spoiler alert, that wouldn't be too much fun. Also, we talked about why we associate the moon with love. That's some more. But it's really, really easy to look up at the sky and find what it contains to be really separate from and beyond us. Honestly, much of it out there is at distances further than we could possibly travel in our lifetimes with the technology that we have now. But there are still many ways that these objects reach us, and we're constantly being bombarded with the light from stars thousands of light years away, and of the light of entire galaxies millions and billions of light years away. They come to us and we study them and write stories about them and songs and movies. There are many ways that we bring this vast universe down to earth, just like we do here on this show. Particularly today, we're going to be talking about other Earths, planets out there that could potentially host life, and what living in a place like it could mean. So this is episode 10, Goldilocks and the Many Dwarfs. And yes, we're mixing fairy tales here, but you'll soon find out why. Some of you might have heard recently that there's been a bunch of Kepler Space Telescope hubbub in the news. So Kepler is a NASA space telescope that, among many things, searches for planets around stars other than our sun. I think we have a wonderful animation of some of the multi-planet systems that Kepler has discovered over the past few years. And so these planets around stars other than our sun, they're called exoplanets. And on May 10th, NASA actually announced that the mission had been able to find 1,284 new exoplanets since its last announcement. And all of these objects, oh yeah, here's the multi-planet system. So we see these are just a bunch of other planets around other stars, and only stellar systems where there's multiple planets. We've also found a lot of stellar systems where there's just been one planet that we've discovered. So this is just a tiny slice of what Kepler has been able to discover. This is it's a crowded image, but that's because there's a lot to be seen right here. And so back to the announcement, on May 10th, NASA announced that they'd found over 1,000 new exoplanets, and all of these objects, all of the ones that they've announced, are over 99% likely to be planets. And so there's also 1,327 other planet candidates that it found to be statistically more likely to be planets than not, but they're not quite at the 99% threshold. And so these scientists are super careful about saying something definitely is or isn't a planet. So they really make sure a planet is the name of the game before jumping to any conclusions. So those other 1,327 possibly planets are not ready to be put in the planet category. But more investigations will follow. And so it's amazing to see these are the type of things that we discover. We'll see maybe where the bundle of potential ends up for the possible planets. But now, let's just focus on the planets that we know to be planets. So as of this show, including Kepler, including all of the other planet watching missions out there, we now have 3,408 planets outside of our solar system that we know for sure are out there. And so this is why the news we heard from Kepler just last week is so amazing. This number brings to light how crazy this is. The new Kepler addition to our known planets now makes up over a third of the total number of planets we know about. And we've been finding exoplanets for 2 decades. And all of a sudden, we've just increased that number this much. Now this new announcement brings a whole new avalanche of planets just right to our doorstep. So how exactly does Kepler go about finding these planets? How did it find all the things we're seeing right here? Well, we've actually experienced the method that Kepler uses right up close and personal in our very own solar system just the day before Kepler made this announcement. On May 9th, Mercury actually crossed the surface of the sun in our view. And this is an astronomical phenomenon known as a planetary transit. And so we're seeing the surface of the sun right here. And if you look really closely, a little bit below the center of the sun and a little bit to the right on your screen, you should see a very small dot. That is Mercury. And so this is wonderful imagery taken by Slooh partner Matt Francis on the day of the transit. absolutely incredible images from his Prescott Observatory in Arizona. So yeah, we're seeing more of that here. And we see that the sun absolutely dwarfs this planet, but it's still something that we can see because of these gigantic telescopes that we use. So this Mercury transit, from our view, what it is it shows a small black dot inching across the surface of the sun. That's what a planetary transit is. And we can also see planets do the same thing around other stars. I think we have a video of a light curve and what an exoplanet quite is. And so just to preface that, we have, when an exoplanet crosses in front of its host star in our view, oh, here it is. So we see there's, like we saw with Mercury and our sun, this is just a hypothetical exoplanet here. We see this circle, this black circle, that's the planet crossing in front of that star. And when that planet Okay, so an exoplanet. Oh, sorry about that. The mic just went off for a short while there. So when an exoplanet goes in front of the star, we see a little dip in the light, and that's what we're seeing in this image here. The brightness that we're seeing from that star dims when the planet is in front of that star, and so this is what Kepler does, is that it looks at different stars, it looks at the light coming from those stars, and it tries to spot dips in that light. And the larger that the planet is relative to the star, the bigger that light dip in the light is going to be. So it's often easier for us to find larger Jupiter-sized planets than it is for us to see smaller bodies. Now, if we go back to Matt Francis's Mercury image for just a moment, we're going to see here that Mercury is, like we saw earlier, really, really small relative to the sun. The sun is absolutely so much larger. We can barely see Mercury on this image. And so if the sun were, say, hollow inside and you wanted to fill it up with Mercury-sized gumballs, you would need over 20 million Mercuries to fill a hollow sun up to the brim. That's an incredible size difference. In comparison, you could only fit about 1,000 Jupiters in the same amount of space. So that brings to light, a Jupiter-sized planet can block more of the light because it's just that much significantly larger than a smaller Mercury-like planet. Even though Jupiters are easier to find, Kepler still does find some Earth-sized rocks out there. One of the 1,280, oh yeah, this is a wonderful size comparison of Jupiter versus, you can hardly see Mercury here in this image. And so out of the 1,284 planets that Kepler just announced, 550 of them could be Earth-like size in comparison. We see, the small little circle there that is Earth. And 9 of those orbit their stars in what is called the habitable zone, which means that they are just at the right distance from those stars that those planets could have liquid water in the right conditions. And so here we're actually seeing a demonstration of what different habitable zones can be. The green areas, they're in a place where it's not too hot, they're not too close into the star so that water wouldn't just boil or evaporate away, and it's not too cold so that they're so far away from the star that the water freezes. The temperature's just right in this happy green zone. And this is why the habitable zone is also nicknamed the Goldilocks zone. The Goldilocks planets are the ones that we're really excited about because liquid water is really important to how life on Earth got started. So we think that liquid water in other places could help facilitate that same life-growing process. So now we've brought up the Goldilocks part of our title. But where exactly do the dwarfs come in? That's actually, it has to do with the stars that we're finding a lot of these potentially habitable exoplanets around. So remember when we were talking about transiting exoplanets, seeing a planet in front of a star and then a light curve that sort of dips when the planet's coming in front of it. How we find these transiting exoplanets is by watching that light dip when the planet crosses in front. And the bigger that the planet is, the bigger the dip, the light we see. But also, the smaller the star is compared to the planet, the bigger the dip we see in the light as well. And so a planet size relative to that of the stars is really important. This is why we often find planets around smaller stars because they're easier to spot. And some of these smaller stars are known as red dwarfs. And here we have a wonderful comparison between different stars. We have Sun, a red dwarf, a brown dwarf, which isn't actually a star, it's sort of a transitional point between the large Jupiter-like planets and the stars. We have shapes and sizes of lots of different things in our universe, quite a varied place. But we see here the red dwarf. It's smaller, it's not as hot, and so there's a lot of things that are going on there. But we do find a lot of our Goldilocks around our red dwarfs. And so these guys can actually be anywhere from a half to less than a tenth of the size of our sun. Where 1,000 Jupiters can fit inside our sun, something more like 100 or less, depending on the size, could fit in a red dwarf. And when Jupiter-sized planets or Earth-sized planets pass in front of these red dwarfs, the amount of light that they block is more significant and easily detectable. And here we're seeing an artist's concept of a red dwarf, and it looks a little bit different from our sun just because it's not as quite as hot, so it's emitting light at different wavelengths, so we're going to see that star as sort of a different color. So also, let's jump back to the habitable zone comparison image again. This image compares the habitable zones of Earth to the Kepler-62 system. Here it is. And the Kepler-62 system, this is not a red dwarf star, but it does have a star that is hundreds of degrees cooler on its surface than our sun. So it does demonstrate the concept of what we're going to go into. This means that the Goldilocks zone for the Kepler-62 system, where it is not too hot or too cold for liquid water, that's closer into that star. And we can see that here in that image, that the solar system, the thing that we see on the bottom, that has a habitable zone that stretches further out from the star, where the Kepler-62 system, which has a cooler star, that green zone is closer in to where that star is. And so this means that if the Kepler-62 system had a red dwarf, say, instead, the difference between habitable zones would actually be even more extreme because red dwarfs can be over 1,000 degrees cooler on their surfaces than our sun. So we'd need that green zone to be even more close in. The planets would have to keep very close to keep warm enough to maintain water. And so with our telescopes right now, it is much easier to find transiting planets close into their host stars than it is to find them further away. And because of this, we often find planets that we think are way too hot to sustain life. Like if we were, say, looking at our solar system at the bottom, finding a lot more that were inside of that green instead of right within it. Closer into the star than that green is instead of right within the green, so to speak. But with the red dwarf stars, that's not as big of a problem because the Goldilocks zone is so close into those stars. So it's easier for us to find planets inside of those Goldilocks zones, which is wonderful. Yeah, here's an artist's conception of one of the close-in planets of a red dwarf system. And so many of the planets that we know of in the Goldilocks zone are orbiting around red dwarf stars. So dwarf stars, they are pretty cool. And I mean that literally in terms of their temperature and of course figuratively when it comes to planet hunting. And if you are still not convinced about this after what we've been talking about here today, let's look at the Slooh live telescopes. So tonight, live on Slooh, we're coming in from the Canary Islands, and we're actually looking at what is called a globular cluster, a cluster of stars. This is M12 in our night sky. This is 15,000 light years away from us in the constellation of our newest member of the zodiac, Ophiuchus. But we're looking at this cluster of stars live from Slooh, and it's showing us in a really sort of head-on way. These star clusters are great because they really throw it in our face, just how many stars upon stars there are out there. Stars are clustering together here, but they're spread throughout our galaxy, and there are hundreds of billions of stars just in our Milky Way galaxy alone. And they're not all the same. Some are larger, some are smaller, like we've gotten into. They have different colors, ages, and different compositions. But one thing that we do know is that a majority of those stars in our galaxy, something like 70%, are red dwarfs. Also, red dwarfs live longer than their bigger, brighter cousins, so when other bigger stars do die out, they keep on burning. This means that we have a lot of different red dwarf targets to look at when searching for exoplanets, and we have a lot of red dwarfs that have been shining for a while, maybe long enough for life to have developed on the planets around them, because we know from our personal experience, life takes a little bit of a while to develop. And so we can find transiting planets around these red dwarfs easily because they're smaller, and we find more planets in their habitable zone because those habitable zones, those Goldilocks zones, are closer in, and we also have more of those stars of these types to look at. It's great, but what does it mean? Us humans, we're not orbiting a red dwarf star, so how would life be different for someone living in a system like that? Could life really exist at all? Well, let's bring it down to Earth. Because the habitable Goldilocks zone is so close into the star, something around the distance from Mercury to our sun, or even 10 times closer than that, it makes it easier to find these planets. But that closeness to the star has its downsides, one of them being an effect called tidal locking. And so this is an effect that our Earth creates for our moon. I believe we have, oh yeah, yes, a wonderful visual here of that happening here. So when we look at the moon at different times of the month, we see different parts of it illuminated. And we're seeing here, the sun's going to be in a certain location, and then we're going to see, as the moon orbits around us, different sides of the face of the moon illuminated because of how the sun illuminates it. And those parts they're always the same side of the moon, though. We're always going to be facing that same side, and the opposite side is always going to be facing away from us. This is because the moon spins around once on its axis every time it orbits around us. And so as it's spinning, it's orbiting, and there's going to be one same side that faces us here on Earth. And now the same sort of thing can actually happen to planets that are very close into their host stars. And so just imagine our Earth being, say, a dwarf star, and the moon being a very close-in exoplanet that's in the habitable zone. So if a planet, say, were to get tidally locked in this sort of situation, crazy things can start to happen. Only one side of the planet will ever face the star. We always see that thing orbiting around it. There's always going to be that same face. And so that means that one side of this exoplanet will have eternal day 24/7, and one side will have eternal night. It will always be dark. This would cause a lot of difficulties for any life trying to maintain a foothold on this planet. The daylight side would bake and the nighttime side would freeze. Goldilocks would just essentially not be having a good time with these dwarfs. Unless large oceans and atmospheres could potentially transfer that warm air on the nighttime side, or to the nighttime side, and then cool air from that nighttime side to the daytime side. If there was enough heat transfer, then maybe something could work out. And we also don't know if there's going to 100% be tidal locking from planet to planet, but this is one scenario that might not be the greatest. But with enough of that heat transfer going on, conditions might be okay for things like, say, plants, to survive. So speaking of plants, though, they would probably look a bit different from ours. They're red dwarf plants. For one, they'd probably look black instead of green. And so this is because a red dwarf star would be giving them more light at low energies compared with the stuff that the plants on Earth get. And so the plants on this alien world would have to try and absorb light at more wavelengths to get the energy they need for photosynthesis. And so yeah, the star is going to be peaking light at different wavelengths. It's going to be emitting light, different energies than our sun would. And so you get different colored plants. And so you know how you never want to wear black, for example, on a hot day? That's because black absorbs all the wavelengths that you see. So the black plants would be absorbing a lot of light. One big problem, though, is that the light coming from a red dwarf star can be a little bit unpredictable, so to speak. Particularly the younger red dwarf stars. For the first billion years or so, they can put out a lot of solar flares that can double the star's brightness all at once in a matter of minutes. Really suddenly. And it can also have periods with lots of sunspots. And sunspots are black, dark regions covering a star that can decrease the amount of light that star is putting out by about half sometimes. These sorts of extreme variations in the amount of light and bursts of solar activity could wreak havoc on the atmosphere of a nearby planet and any of the life living on it. Although perhaps an older red dwarf star that's a few billion years old might make for a calmer, more reliable living environment, so to speak. And so one of the new exoplanets, actually, that was announced last week by Kepler is Kepler 1229b, a planet a little larger than Earth, orbiting in a habitable zone, a Goldilocks zone of a 3.7 billion year old dwarf star, like, say, this one, about half as large as our sun. So discoveries like these are so exciting because with them comes incredible potential. We see a planet in a spot where it could have liquid water and maybe even life, despite the challenges orbiting a red dwarf star could present. And now that we have this target, we can keep looking at this object with different telescopes. When the James Webb Space Telescope comes online in a few years, we could try and use the scope to see if we could spot an atmosphere around this planet, to see if we could spot signs or markers of life. Maybe with this discovery amongst the bunch of 1,284 exoplanets, perhaps we will someday find that we've got our eyes on a planet that's been teeming with life. Or perhaps we'll find a planet where the red dwarf star has been making life such a pain that aliens have decided to go elsewhere, like, say, the skies of Portland, Maine. Last night, the Portland, Maine Police Department actually posted this video of a meteor or alien spaceship that streaked across the sky. Perhaps any visitors here will enjoy the lobster better on this side of the galaxy. Oh, there they go. Vroom. It's quite an incredible thing that they saw there. At any rate, ending with Portland, Maine, that's pretty much the end of our show here tonight. I'll actually, though, be leaving you with a video of thousands of Kepler planets that have been discovered over the course of the mission. The circle, the circle around the star that you're going to see will be the orbits as they would be at the distances of Mercury, Venus, and Earth. This is for comparison for you, so you'll be able to see just how many planets we keep finding close in to our host stars, just how close in a majority of these planets are compared with our solar system. And so showing you sort of what red dwarfs could mean in terms of what we're already starting to find. But now, thank you so much for joining us this evening for Down to Earth, back for the first time after a while. So this has been Eric Edelman. I hope to see you again next week, same time, same place on Slooh.